Hello everyone, my name is Nikola Pokorny and I would like to introduce you development of photovoltaic-thermal collector here in UCIP. I'm part of the group which is focused on energy systems in building. And what is the motivation? Photovoltaic panels on the market are able to produce electrical energy with efficiency from 10 to 20%. That is because 10% of incident solar radiation is reflected and quite a huge amount of energy is wasted into heat. So it is a logical way to combine two conventional technologies, photovoltaic panel and solar thermal collector. Thanks to this solar device, we can maximize utilization of incident solar radiation, and from limited roof area we can produce more energy than by side-by-side conventional system. Nowadays on the market there are mostly unglazed PVT collectors which are convenient for low temperature applications from 10 to 30 degrees Celsius. Originally, the unglazed variant of PVT collector was developed because of the cooling of PV absorber, and thanks to it we can a little bit increase the electrical efficiency and lifetime of the PV part. But nowadays a lot of different applications with unglazed PVT collector exist, like heating of swimming pool or combination with primary circuit of heat pump. Here in UCIP we are focused on glazed variant of PVT collector, which is convenient for high temperature applications around 60 degrees Celsius. So it's convenient for domestic hot water preparation, which is the most common application in the world. And glazed PVT collector can compete with solar thermal collector because the heat production of glazed PVT collector is comparable to solar thermal collector. And the glazed PVT has advantage of secondary electrical production compared to solar thermal collector. Okay, and why is not glazed PVT collector widely on the market? Because conventional PV panels on the market has PV cells encapsulated in ethyl vinyl acetate lamination, and the maximum temperature of the EVA lamination is about 80-85 degrees Celsius, but glazed PVT collector stagnation temperature is much higher. It's about 150 degrees Celsius. If the temperature is higher than the maximum temperature of EVA lamination, the EVA starts degrade and we can expect corrosion of PV cell contacts. And the lifetime of the PV is shortened, and of course the electricity power is reduced. Due to this fact, the current trend of the glazed PVT collector development is divided into two ways. The first way is focused on the overheating protection. These three concepts are, I don't see the mouse. These three concepts are based on the PV part laminated in EVA. And during the stagnation, I don't see the moving. During the stagnation, the absorber is moving up, and the temperature in the collector is lower. The second concept is based on the ventilated channel under the absorber. And during the stagnation, the ambient air is flowing under the absorber, and the temperature in the collector is decreasing. And the third concept is based on inflated layer, and during the stagnation this layer is deflated and the temperature in the collector is lower. Here in USEEP we are focused on replacement of EVA lamination by polysiloxane gel, which is in the space between the glass pane and the copper absorber where are PV cells encapsulated. And this concept is patented and is based on the double glazing, which is on the layer with the polysiloxane gel, and the polysiloxane gel layer is on the copper absorber. Here I would like to share with you some results of performance analysis of goal application. The goal application for PVT collector is preparation of domestic hot water, and here is one multifamily building with 45 flats, and we did a simulation for Prague climatic conditions with some heat demand, electricity demand, and we did this simulation in Transys. Ideal buildings for PVT collectors are with high heat demand and limited roof area. And we did the comparison for conventional system consists of photovoltaic panels and solar thermal collectors, 50% of photovoltaic panels, 50% of solar thermal collectors, compared with the PVT system consists of 100% of area covered by the PVT collectors. And if we compare the annual electricity production, we can see that it's 1.3 times higher compared to the conventional system. And if we compare the thermal production, we can see that it's 1.5 times higher. We compared different ratio on the of the conventional systems. For example, 10% of PV, 90% of photothermal, or 10% of photothermal and 90% of PV, etc. And in all ratios of conventional system, the PVT wins. Here I would like to show you how it looks on the market. That we can see that all of PVT collectors on the market are lower compared to state-of-the-art conventional solar thermal collector. That is because of simultaneous electrical and thermal production. And here I would like to show you the thermal efficiency of UC prototype, which is much better compared to the market, but there is still some difference compared to efficiency of state-of-the-art solar thermal collector. And here you may see a comparison of electrical power compared to the market, which we have a little bit lower, but this is because of backing factor, which is 62% of gross area covered by PV cells, and this number can be considerably increased if we change dimension of the PVT collector. Okay. We manufactured a lot of different PVT collectors. We tested them under steady state condition thanks to solar simulator in USEEP. We tested several prototypes under real climatic condition in solar domestic hot water application for several months. We also did some research focused on integration of PVT collector into a facade module. We tested this prototype under steady state condition, and also we did measurement of this facade module with integrated PVT. This is the long-term measurement for almost 2.5 years with very promising results. I thank you for your attention. If you have any question, do not hesitate to contact me or to visit me in my office. Okay, that's all from my side. Thank you.